When we multiply a row matrix by a column matrix, we multiply the first number in the row by the first number in the column, the second number in the row by the second number in the column, and if that's the end of our row and column, we add those two products. So we have 2 times 4, 5 times -3, and we add those up, and I believe we get -7. Now, again, this is called a row matrix. This is called a column matrix. We can always multiply a row matrix by a column matrix, provided we have exactly the same number of entries in the row as we do in the column. If we have more than, let's say we had 3 numbers in the row and only 2 numbers in the column, we wouldn't be able to do it because we wouldn't have anything to match up with the third number. And similarly, if we have 3 in the column and only 2 in the row, we don't have a third number in the row to match up with the third number in the column. Everything has to match exactly. Everything in one has to match everything in the other. Okay, has to match something in the other. Okay. Now we do what we call a 2 by 2 matrix. It's got 2 rows, a row here and a row here. We can multiply this row by this column, and we get this result, the same result we got before. We multiply this row by this column, and we get 3 times 4, -1 times -3, and that adds up, I believe, to 15. Correct my arithmetic if I'm wrong. Now, we put these, since we now have 2 rows, we're going to want 2 rows in our product matrix, so we have 2 rows in which to put our 2 results. The first row times the column will give us the result in the first row. Second row times the column will give us the result in the second row. So what we have here is a column matrix because all these calculations just come down to a single number. Each of these calculations just comes down to a single number, and giving us what we clearly see as a column matrix, -7, 15 here. This is kind of spread out, doesn't look exactly like a column matrix, but since these calculations all represent since each of these calculations represents a single number, we call this a column matrix. Okay, well, we multiply now a matrix, a 2 by 2 matrix, 2 by 2 meaning 2 rows, 2 columns, by the column matrix XY. What do we get? Well, following the pattern, first number times first number. We don't know what this number is, but we let it, it's a variable number represented by x, so we're going to have 2 times x, giving us 2x. And then we have to add what we get when we multiply the second number in the row by the second number in the column, giving us 5y. And then multiplying the second row by the column, we get 3x and -1 times y, 3x minus y. Okay, so we see that we can multiply 2 by 2 matrix by column vector with 2 elements in it and get a column vector, a column matrix, column vector. We call this a row vector as well. We could call this a column vector. We can call it a vector if it's just got either 1 row or 1 column. As soon as it has more than 1 row and more than 1 column, it becomes a matrix. So I might use the word matrix for a column vector. Or, I might use the word, I might use the word column vector instead of column matrix. And I could use the word row vector. Hopefully that doesn't cause any confusion right now. Now, what we have here, where we have something very much like this, but we set it equal to 2 numbers, a column vector consisting of 2 numbers, is what we call a matrix equation. And a solution to this matrix equation is a value of x and a value of y that makes this true. That makes whatever we get when we multiply 2, 5 by the column x, y equal to 7, and what we get when we multiply the row 3, -1 by the column x, y, and we get -6. Okay, so x, y, a pair x, y is a solution if it satisfies this equation. Now, we could say then that this equation could be written as, well, since 2, 5 and 3, -1 multiplied by x, y is 2x plus 5y, 3x minus y, as we saw here. that this equals this. Now, these two are equal if the first number in the column here equals the first number in the column here, and the second number the second number in this column equals the second number in this column. Now, this equal this just says 2x plus 5y equals 7, and this equals this means 3x minus y equals negative 6. So all of a sudden we see that we can use matrix representation to represent a system of equations. So this matrix equation is completely identical to this system of equations. So, can we write this system as a matrix equation? Well, people didn't have any trouble doing this once we were through this. We got 2, 3, 4, negative 5 multiplied by the column vector xy equals negative 2, 18. Meaning, of course, 2x plus 3y here has to equal negative 2. And 4x minus 5y has to equal 18, giving the same as this equation. Now, the form of this equation, somebody asked why we're doing this. Okay, I see what to do, but how does it fit in? Good question. And you're not going to completely see the reason today, but I will say, I'll answer that question by saying the form of this equation is AX equals C, where A stands for the matrix, X with an arrow over it. When you put an arrow over a symbol, you're usually expressing the fact that now this thing is a vector. Okay, and I said before that XY could be a column matrix or a column vector. So XY is a column vector, so that the X vector here is equal to the column vector XY. And then your C vector is the column vector negative 2, 18, which has been kind of smudged. Let's fix that. Okay. Now, how do we solve an equation like AX equals C? Well, you say, well, we divide both sides by A. Well, yeah. With matrices, we can't really divide by a matrix, but we can multiply by the inverse of a matrix. So instead of dividing by A, we multiply by A to the negative 1, which would be like a reciprocal, but A to the negative 1 isn't a reciprocal. It's an inverse. So we multiply both sides by A inverse, and then A inverse times A kind of goes away, gives us an identity, and we need to be more specific about that, but not right now. Just understand that A inverse times A is an identity, so that leaves us X. And then A inverse times C, well, A inverse is just a matrix. If we multiply it by our C vector, we're just going to get two numbers. Well, one of those numbers, those two numbers are going to match the vector X. The vector X consists of the numbers X and Y. So whatever two numbers we get when we multiply A inverse by C, whatever our column is, the first one is going to be our value of X, the second of our value of Y. So that's kind of where we're heading. It's just that right now we haven't yet gotten to the point where we have any clue how to find the inverse of a matrix. But one thing I'll tell you, we don't find the inverse of a matrix by taking the reciprocals of all the numbers. That doesn't work at all. So it's a little more subtle than that, and we're going to have to develop that, but we're going to get that. And that'll probably be about the last thing we do in the course, as a matter of fact.